Going live. We're live, and what are we doing today? We are trying to solve the LeetCode problem from the top interview 150 list from LeetCode. And this one, let me share the screen. We picked one from the, I picked a problem from the graph category. This is problem number 133, which is one of the early problems, I would say. I don't know exactly what it is, so I just saw that it's early and that it's about cloning a graph. I don't know the problem. So let's see. So there are examples, and let's see if we can solve it or what we can do in about 30 minutes. Given a reference of a node in a connected and directed graph. Okay, we have a node reference pointer to a node. Okay, so there is a node with value and neighbors. It's a list of other nodes, neighbors, connected, adjacent nodes. Connected. Return a deep copy, clone of the graph. Each node in the graph contains a value and a list of its neighbors. Okay, for simplicity, each node's value is the same as the node's index. Okay, for example, the second, so the graph is represented is using an adjacency list. Adjacency is a collection of Okay, in the test cases, they're represented like that. But we do need to return a node. So is a collection of unordered lists used to represent a finite graph. Each list describes a set of neighbors of a node in the graph. A set of neighbors. The given node will always be the first node with value 1. Okay, that's what we get. You must return the copy of the given node as a reference of the cloned graph. Okay, so we have this node number 1. Okay, let's look at this test case. 1, 2, 3, 4. Original graph. You can't return the same graph. 1, 2, 3, 4. This looks like a clone. The nodes are new. The graph looks the same. The nodes were cloned 1, 3, 2, 4, but the graph is messed up, doesn't have same connections. Okay. Okay. Okay, number of nodes in the graph is in the range. Okay. Okay, so constraints. Number of nodes in the graph is in the range, so of 0 to 100. So there could be actually 0 nodes. Sometimes it helps to have if node is nil, return. Yeah, if node is nil, return nil. But yeah, and this is an empty graph. Doesn't have any nodes. Or we can just say return node. I don't know. Maybe that will work, but I don't exactly know how they judge, how they evaluate if you've created. So how do you know if that's a clone and not the original one? I mean, now you can, the easy way would be just to look at the pointers. Yeah. It will be different pointers. Yeah, the memory address. Memory addresses will be different. I guess, yeah. Right? That's Okay, no, the values are up to 100. Is unique value is unique for each node. There is no repeated edges and no self loops in the graph. Okay, so that self loops, yeah. Example, the graph consists of only one node with value 1. And it does not have any neighbors, by the way. So you should return, there was one node. Oh, so you need to return a clone. Yeah. I think, yeah, logically, I would assume to return a clone. Is connected and all nodes can be visited starting from the given node. Okay. So how do we go over a graph? We can do, I mean, we do need to visit all the nodes. And rebuild and clone them. Yeah. So at some point, we'll be looking at a node and its value, and we will create new, and yeah, we'll be looking at a node, and we will have new node where we'll have a clone, which value, yeah, we'll create a clone. Yeah, we'll create clone is new node. Yeah. So overall, is this a big problem to clone a graph? What we need to do is, yeah, you need to create a clone, create a node. And then also create its neighbors and connect it with them. Can we do that with a depth first search? So we will go from 1 and look at like its neighbor 2. We'll create a 1. We'll clone 1. We'll start creating its neighbors one by one and connecting those neighbors but with the DFS we'll create 2. For example, if we start with 2 and We'll create 2. But I'm just thinking, so when we look at a node, when in our call, in our function, recursive call, we'll be looking at one node. So when do we do the connections? I mean, we create this new clone whenever this is called, but when do we connect it to its original neighbor, right? And by the way, I think it looks like they are undirected, so they're all connected. So like 1 is connected to 2 and 2 is connected to 1. So yeah, but I just thought, what if there's an easier way? I mean, we just go over whatever traversal we do, and we just go over, let's say we do DFS. So we'll look at this node 1. And okay, we cloned it. Now, next step we need to do is look at its neighbors. And okay, we cannot fill up its neighbors until we actually create them. Yeah, they need to have we need to create them, then we'll have that address and their address, that memory address, and they will be filled in the neighbors list. It might be like that, right? Yeah, I mean, and like, yeah, so that suggests that unless we want to come back to this node 1, you probably want to go breadth first search. So like we are at node 1 and we'll be looking at all of its neighbors. Yeah, let's do BF breadth first search. Or BFS is going to be a function of, it's going to get a node of type node, and I don't know if it needs to return anything. So that will be, so we initially just say that we declare the variable. Now we will say that this variable is that function. And here we define the function. Oh, wait a second. Totally forgot. Typically when I did BFS, I do it with not a function, but I do it with loop. Yeah. So we'll create a queue. A queue will be a type of slice of nodes, and it will have node in its and for length of length of queue 0, we'll be doing that. So neighbors count or neighborhoods neighborhood size is length of queue and we will go over the neighborhood. Can I spell neighborhood? Neighborhood is not really all the neighbors, right? Is it really all the neighbors? What means neighborhood? What is the definition of the area or region around? Area, okay, so, well, we can mean, I'm just thinking about naming. But basically it's neighbors count or neighbors size. Right? Neighborhood size will be that. And for range, so we'll be going over this neighborhood, all the neighbors. And and what? So and yeah, we're looking right now at the neighbors of right now we have this one node, and we'll be going over that one node. All right. One node. Okay, so now this is Q0. Yeah, so we're taking that node from the queue. Q is Q1. So now we have our queue now, our node now. And here we create a clone. We clone the node. And well, at some point we'll be going, because right now we'll be going over. So we created that node, that clone. We should connect it to some previous node, but in this case it's like it's like empty. I mean, we didn't, yeah, but because what we're supposed to do now is for this node, this is a neighbor of our original node, but we don't have this original node. Yeah, so we need to like somehow what if it's like, okay, we got that Oh, wait a second. No. We queue them up at this point. So for this node, yeah, but this, yeah, we do two things here. One thing is, oh, wait a second. So if we do have a node, I think we should clone it first, because that, we might need two queues here. So I feel like we might need two queues. So we'll have queue of originals, and we'll have queue of clones. And that will be a clone, originals and clones, yeah. So as long as the originals is not empty, so we have that. So now we have the neighborhood. And now we have queue of originals, yeah. So we have it, our now. And so the original now and we have the clone now, right? Why do we need a second queue? I wonder. If we have a second queue, I'm looking at different ways to kind of do that. I wonder if we actually need a second queue. We'll look at one node. The only problem right now is, sub-problem is, we could easily connect it to, but we need those addresses first to its neighbors. But we need their memory addresses, references to them first. So Is that the only subproblem here? The only subproblem, but we do want to take care of it within that. Because in this logic, we're looking at each node when we go over the neighbors. And the only problem, I think we were kind of going somewhere, but the only problem is this an original one, this first node, what they call it, given node, it didn't come to us through some other neighbor. So we didn't know what to connect to it. And I'm afraid this yeah, I don't, let's scale back. I don't think we need the copies of I think we might be good with without the clone. Without the cloned let's start simple, yeah. Without the queue for the cloned ones. Yeah. Just nay size. Nay size. So we're looking at this first node. We created its clone. And we want to connect this clone. We need to do two things here. And by the way, when we create the nodes, that's the moment we have their addresses. So like this clone right now, we're just looking at it, okay? And if we so, I mean, if we move our pointer to a new one, we'll lose the address of this clone. And we need those addresses when we have this first node. This first node, when we have it have second node. I guess what I'm thinking about is, yeah, this is the time when we're looking at the second node, the time to connect it, to let well, but I mean, we have in the queue the original ones. Yeah, let's start simple. Let's see what we actually need to add. Maybe we just need some little tweak. So this right now, this creates a clone with the value. Okay. And we're going through the list of the neighbors. Wait a minute. Wait a minute. Wait a minute. So this is the list. The one is the list of the neighbors initial. There is, yeah, we're supposed to, yeah, we need to know what to connect them to. Yeah, so we created this one. Yeah, we created its clone and we need to connect it to the original. Let's say, yeah, in the next iteration, what will happen? Oh, we need to queue them up, by the way. All the neighbors of this one now need to get to the queue. So this now neighbors, if I could spell neighbors, we need to go over those. That's a slice. So we're going over the neighbors of one. And what we're doing is
outlets in the chairs and also in the conference table, and then we do offer free Wi-Fi.
Putting them in the queue.
Okay.
So the queue is append queue, and then this neighbor. Right? Right. So queue plus this neighbor. Okay, so that gives us all the neighbors of this node. And by the way, this looks like a good moment to connect them. So yeah, we have this neighbor. We know this neighbor is with now, so why not why don't we create why don't we create clones here? So that one is called now clone. Yeah, let's call them like that so we don't. So we have now clone. And by the way, that is called now value. But here we'll have a clone. And we're gonna put the value in it. And we're gonna connect. We're gonna say that now. Now neighbors. Now clone neighbors is append now clone neighbor. Oops. Yeah, we're gonna add now clone neighbors. I'm gonna append this clone, yeah. I think it's like something like that. So what this will do, it will create for each node in the queue, it will go over its neighbors. So 1, we're going over its neighbors, like neighbor 2. And we already have a clone, and we're connecting. Yeah, we're cloning them and connecting them to the clone. Yeah. But now we don't need, the problem is we don't need to create it here, definitely. Why? Because we are creating them here. Yeah, we will also already have the 2 and 4 are created here, the clones, I mean. So when we go over them in the queue, we don't want to copy them, create them again. So let's give it like 4 more minutes, but overall, if we take a step back, I feel like so we have the clone. Next time, what will happen? So now we added them as their neighbors, but just this this now clone is. That's why I feel we need the clone queue also, because we need to queue them up also so that we can later connect to them, right? Because we have now for the original, but we need the now for clone, which will be in the queue. Yeah, so that's why we need not only the queue, but we also queue clone. And that will have the clone. Clone node, basically, but so now we have something in the queue, of original. Now we need clone now, or current. We can call it This is Q, this is Q clone. This is clone Q, I think. Yeah. And by the way, we'll be returning the clone. Yeah, clone Q. And we have now from the Q, we have clone now from clone Q, yeah. Yeah, so we're same thing. Need to do the same thing. This dequeuing. Okay, so a little bit of a naming game. So we're going over the neighbors of now. And yeah, we're appending them to the queue to take care of its next. Here we create the new this is clone Q, this is clone now, this is clone neighbor, clone nay. And we're gonna say that. So we created a new neighbor, cloned. But yeah, then the value, we signed it the value. And this clone now, we're connecting it. Yeah, clone now is clone neighbor, yeah. And we also need to, so this clone neighbor, we need to also enqueue it. So we'll need to say that clone neighbor is append queue clone nay. So we can take it, yeah, then. So this should be something around somewhat, we should be somewhat close to the solution. We're going, yeah, we're just repeating everything. And so what that should do, let's try and test this. Oh, clone is, yeah. Clone val now, val. Oh. Node, yeah. Node val. Okay, we ran out of time. Well, we are running out of time. It's 43. I feel we're pretty close, but why would we run out of time? As we go through that, like one will get their neighbors, then this one will give us all its neighbors. I'm afraid we will be circling around. I mean, forget about cloning, just traversing this graph. Breadth first search. Like 1 will give us these 2. Yeah, but we need to track the visited. Yeah. Otherwise, 2 will give us 1 again. Which we actually do need to get when we take care of 2, when we have 2 on our, when we're working with 2, yeah. And we'll be looking at 2 now, will be 2. We'll say that, yeah, and we'll be looking at its clone. We do need to connect 2 to 1. Or another way would be when we connect, 1 to 2. When we connect 2 to 1 here, when we do that, we might also at the same time connect this clone neighbor, clone A, not only now, but clone A neighbors also should be connected to clone now, so that, yeah, so that 2 is already pointing to 1. But when we do go get to 2, we don't want to repeat that. So we need to, yeah, visited is the solution to that. A list of visited, we need to have visited is a make map of type node references to. So node, and yeah, whenever we'll have a node, we need to say that, okay, visited now is true. And when we go over, yeah, we don't want to, if visited, so if not visited nay, then we do this. Oh, otherwise we don't care, yeah. Or because now we'll, yeah, so at least we got rid of the loop, just infinite looping, and output return a copy of all the nodes in the original graph. You must return. So what we're returning is the clone. And that clone goes into our clone queue, which will be our clone now. What's wrong with the... Yeah, so we are returning pointer to a node. What's wrong with it? What doesn't it like? Output, you must return a copy. And clone is a new node, okay? A pointer to a new node. We clone value. Is that. So we'll be looking at it. It's here, clone now will be that. And this clone now will get its, it will be connected to all its neighbors. And each of its neighbors will be connected to it as well. So here, clone now neighbors will get, yeah, this clone neighbor 2, neighbor 4, and they will have this connection in the mutual connection. And when they get that mutual connection, I mean, we return the clone. What's wrong with the... So this clone is connected. Must return a copy of all nodes in the original graph. We don't see the problem because it looks like it doesn't show us what's the problem. It doesn't show us the... I mean, do we need to do anything else? So after we connected to them, so this clone now is gonna be connected to gonna have all its neighbors, Or, I mean, we can see clone now neighbors. T print line. Let's just print clone now neighbors. Let's print and see what they have. So this first, the one, and by the way, in value, please. Clone now, and clone now neighbors. So first one has 2 neighbors. Second, for some reason, has 3 neighbors. Wow. So first one is pointing to I mean, to clearly see what these neighbors are, we need to print them. Not like that, but we need to print them. So for nay range neighbors, we wanna print nay val. Yeah, I want to print their values. And yes, so one is it's a bit too confusing. We need a line break after that. We need a line break. Oh, that's the print. That's like a next line. For each. Now we need that line break just after the well, if I want to see the clone, then value, then I want to see its neighbors separated by comma, and then I want to have an empty line break. Yeah, just okay. So that's what we have here. So one is connected, right, but two is right, but it has three several times. It got 3 is to 4. And then it's 3 is to 4. Okay, so some of them got appended, like 3 got appended twice to 2. So we do connections only if they have not been visited. And whenever, when we got 2, so 1 is visited now. When we got 1, it was visited. Yeah, all of its neighbors one became, wait a second, when do we, so 1 is visited unless, we go over the neighbors of 1 and check if they have been visited. So they have not, so 2 and 4 have not been visited. So we connect 2 and 4 to 1, so mutually connect them to 1. And the only visited at this point has been 1. But the 2 and 4 are now queued, and in the next iteration we'll look at 2. So 2 is now visited. 2 will be going over its neighbors. And it will not relink, so again with 1. So neighbor 1 will not be, but 3 will be a new neighbor. 2 will go over its neighbors, will create 3, and 3 will become, oops, the neighbor of 2. I feel like we're close. There is a bug, but it looks like we need to find that bug, and it might take some more time. So it's a good try. Thank you for watching. See you in the next. Yeah, see ya. Because we're running out of time.